Hi, welcome to CS70 Video Solutions for Homework 5. Sorry for the delay, but let's get to work immediately. So, right here I've pasted the Fermat's little theorem, FLT, and you'll quickly realize that Fermat's little theorem is very useful in solving these types of mod problems. And let's just demo with number 1. So, 571 should strike you as weird, because it's a really large number to deal with, but also if you just run through the list of other primes to see if it divides, 2 doesn't divide 571, neither does 3, because the digits add up to 13, which is not divisible by 3, and likewise for 5, and so forth, and then you realize that 571 is indeed prime. You can just run through the numbers really quickly to back up your intuition. So this is, primality is really key because it means we can use Fermat's little theorem. So let's construct Fermat's little theorem. We can choose any A. So, right, any A between 1 and 570, we can see that this is most helpful to choose A equal 569, and P is of course 571. So FLT says that 569 to the 570 is equal to 1 mod 571. You can see how this result is beautiful. It's like a piece of art because such a large power becomes such a simple number with mod. And that is the beauty of Fermat's little theorem. So, how do we use this in our problem at hand? Well, if you notice, these numbers are really close to each other, which should give you a hint. But 569, you can factor out 570 times 570 to the 570. You can factor out a 570 because there are 571 factors. And it makes no difference what you do with those factors. And you'll realize from your exponentiation rules, you can compute this directly, but exponentiation might be a bit more clear, that multiplication of the exponent looks like this. And we can eliminate our expression to 1, and we're left with 570s. 1 to any power is 1, so we're done. So we use the two beautiful facts, one from the FLT and another from the fact that 1 to any power is 1. Excellent. So that is how you use the powerful Fermat little theorem to solve part 1. Now, before I move on, I need to make a note here. The number one most common mistake in doing these mod problems is to think that you can eliminate this 571 and just go with 570 because you're in mod 571. Why does this not work? The reason is that you can't use mod. So do not use mod on the exponent, because the exponent doesn't really interact with mod at all. It's the base that interacts with the mod. So you can modify the base, but you don't know what the exponent will do to the base specifically in the context of mod, so make sure you do not make this mistake. I'm pretty sure it's the number one mistake you can make for these types of problems. Excellent. So moving on to part 2, I'll give you a moment, like 2 seconds. Now problem 2 is a little bit trickier. What you have here is 9, which is not prime, which means that you cannot use the FLT. So now that we're stuck with nothing in our arsenal, what do we do? Well, there's another method in modular exponentiation called exponential squaring, And basically how this works is, suppose you have a number a. If you square a, this is perhaps congruent to some b, mod p. Now this b is the same as a squared, so if we square b to get a different number c, then this c is congruent to a to the fourth. So you can see that by repeatedly squaring and simplifying, repeat squaring and simplifying, you can see that we get from a squared to a to the fourth to a to the eighth and so forth in just a few number of calculations. So we should use this to solve problem 2. So here we have 5 to the 8 to the 11. Let me rewrite this. Since you know 8 is 2 to the third, 8 to the 11 is just 2 to the third to the 11, which is 2 to the 33rd. So 5 of 2 to the 33rd power is equal to, again, we factor out a 2. So we factor out the 2. We're left with 2 to the 32. And now the 5 squared is 25. 25 mod 9 is what? So pick the biggest multiple that's less than 25, which is 18. So subtract that, you get 7. So it's 7 mod 9. Cool. So now we're at 7 squared to the 2 to the 32. We repeat this factoring. You'll see this is very tedious, but in a moment there's a saving simplification, which is equal to 7 to 2 to the 31. And 7 squared is 49, which is 4 mod 9 from 45, right? And then this is just 4, congruent to 4 to the 2 to the 31. We rewrite this again. And now 4 squared is 16 mod 9 is equal to 7. So now we have a loop between 4 and 7, which is amazing because this simplifies our lives by a lot. So now that we've established this, we now take a look at the pattern. So 7 to the 2 to the 32 is equal to 4 to the 2 to the 31. And so if we keep going, then we'll eventually reach 7 of 2 to the 0, right? Because for this number is if this number is even, then we know that 7 is the base. And this is all very systematic because we went through and factored each 2. So 7 to the 2 to the 0 is just 7, 1, which is 7 mod 9. And that is your answer. Excellent. So if there are any doubts, please leave a response in a Piazza thread about my video solutions. You can just type in video solutions and leave a response there. I'll be checking. So now this is part 3. We see that 31 is prime, so we can use the FLT. Let's celebrate right now, yeah! But our work is not done yet. So we can just choose a random number A. This A equals 7 will help us most here. And P is, of course, 31. FLT tells us that we have 7 to the 30 equals to 1 mod 31. However, we can't just replace anything here, unlike what we did in 1, right? So we need to do some additional work. First, we want to see how we can divide 2014 into pieces of 30. So our problem, right, is we want to transform this initial power into all these little pieces of 30 plus the remainder. What does that look like? Well, we've been working on it this whole time. It looks like a mod. So this is in fact 7 to the 2014 mod 30, and this only works because of the FLT. from the FLT. So 2014 mod 30, if you do the math really quickly, you have 6 and you have 21. 7 looks like the right one here. So you're left with mod 4. Or 4 mod 30, sorry. Mod 30, mod 31. And now 7 to the 4th we can use exponential squaring. So 7 squared is 49 minus 31 equals to 18. So this is congruent to 18 mod 31. So you should use congruent when you do a modulo operation, but it's really easy to miss. So I won't go back and change those now. I'll just keep pressing on. So this is 18 mod 31. In order to get 7 to the 4th, it's just 7 squared, which is 18 squared. Now 18 squared equals to 20 times 16 plus 4. And this is 324. So this will give us 18 squared is 324, which is congruent to, now you can just pick 310, right, to subtract. This will give us 14 mod 31. And this 310 I derived by inspection. It's the closest 31 multiple to 324. So this is our answer here. This exponentiation trick is basically 20 minus 18. So the number you have times the biggest 10, right, squared. So this is 2, and 2 squared is 4. And then you can just do 20 and also 18 minus 2, which is 16. But anyway, that's just a fast arithmetic trick. The main thing here is we can generalize from Mott's little theorem to tell us that we can have a to the k mod p minus 1 mod p if p is prime. Or a to the k equals a to the k mod p minus 1. And this is just easily derivable from Fermat's little theorem, but it's a really handy shortcut because it basically summarizes what we're doing here when we've split up 2014 into these little pieces of 30. Excellent. So that is problem 1.